Good day to all of you. Today we shall discuss on Model Question Paper 1 with effect from 2023-24, that is current year. CBCS scheme, 3rd semester BE degree examination, Digital Design and Computer Organization with subject code BCS302. The question number 10b. Write and explain the control sequence for the execution of an unconditional branch instruction, that is asked for 10 marks. Our sincere acknowledgement and thanks to author Karl Hamacher of the textbook with title Computer Organization 5th edition. The whole content of my discussion I have taken from this book. So figure 7.7, what is taken here? Control sequence for an unconditional branch instruction that shows 5 steps of control sequence which is needed for the execution of unconditional branch instruction. So as to understand this, we need to understand first single bus organization inside the processor. Figure shows single bus organization of data path inside a processor, or it can also be called as single bus organization inside a processor. In this figure, PC means program counter. This register always stores the address of next instruction while processor is executing a program. MAR means memory address register. It holds the address of memory with which processor is doing read or write operation. MDR means memory data register. Through this register, processor does read or write operation. Means when processor sends a word to memory or takes a word from memory, through MDR only it takes. This is arithmetic logical unit which does arithmetic and logical operations. This is instruction register which stores the instruction that is fetched from memory into the processor. Instruction decoder takes the instruction from instruction register and decodes it. Means it assesses what operation must be done and where are the operands. Accordingly, control logic generates control signals which are sent to different parts of the processor, and with this it can control and coordinate the activities of the different parts of processor. This Y, Z, temp are some intermediate registers. R0 to Rn-1 are general purpose registers which are used for temporary storage of some data during execution. Apart from this, there are some special registers like index, stack and accumulator registers which are used for some special functions. And this is all about single bus organization of the data path inside a processor. Next we shall see input output gating for registers. So input output gating for registers means how to store a word in register, means input a word to register or what is contained in the register to take out. To do input output operations with registers with the help of signals, that is called as input output gating for registers. Here for example, if you take MDR, that is memory data register, which is between internal processor bus and external memory data lines. Suppose from processor register here, if data is to be sent to memory, first that is put on internal processor bus. Then the data from internal processor bus, it is going to be stored in MDR by giving MDR in control signal. Then this data goes to MDR. Then MDR out E signal is given. Then that data is passed on to external memory data lines. From here it is sent to memory. So this is memory write operation done from the processor. Next, from memory if it is to be brought, so when memory puts on memory data lines, MDR in E signal is given. Then from external data lines it goes to MDR. Then MDR out signal is given. From MDR it is put on to internal processor bus. From here it is taken to any register. This is a read operation done by the processor. This is how for doing input output operations with the MDR through signal MDR in, MDR out E, and MDR in E and MDR out is called as input output gating of MDR register. If you take up any register, say R0, R1 or say RI, any register. So here this is internal processor bus. So this part is just magnified here. So internal processor bus data is on that. Then RIN signal is given. Data from the internal processor bus is inputted to register, means it is stored in register. Suppose content of that register has to be taken out and put on to processor bus. ROut signal is given, then the content of that register is put on to processor internal bus from where it is given to other registers. This is how using control signals, that is in and out signals, the input and output operation with the register is done. That is what is called as input output gating for registers. Now we have understood single bus organization of the data path inside a processor and input output gating for registers. Next we shall see to an example for branch operation. After that we shall come back to the explanation of control sequence, 5 steps of control sequence needed for execution of unconditional branch instruction. Okay, so when processor is executing branch instruction, PC will be holding next instruction address, but in branch instruction offset is specified, that is 46. It will be stored in index register, that will be added to next instruction address that is 2004 plus 46, it will be target address 2050. Hence the program will not jump to next instruction, but program control will be made to shift to 2050, that is target address. That is what is the effect of branch instruction. If this action takes place without checking any condition, then it is unconditional branch instruction. If it checks any condition, whether A equal to B, A not equal to B, or less than 0, greater than 0, any such conditions, for that it will be checking condition code flags, okay, bits in the status register, and then it performs shifting of program control from next to target address. That kind of branch instruction will be called as conditional branch instruction. So program control is going to jump from 204 to 2050. Plus 46 is done. The number is positive, plus 46. It may be negative also. Here if you consider this program, so the loop label is here. So branch greater than 0 means condition is checked. If it is true, it will jump back. So by 1, 2, 1, 2, 3 instructions back means minus 12. The offset will be minus 12 here. Here the offset is 46 plus it is. Here the offset is minus 12, negative it is. So it depends on the offset given by the branch instruction. In case of loop label, here by the branch instruction offset given is minus 12. Here by the branch instruction offset given is plus 46. Okay. But here in this case it is conditional, branch greater than 0 means only if it is greater than 0 it will shift the program control back, otherwise it will come next. Here no condition is checked, simply it will shift the program control, instead of next instruction to, it will shift it to target address. In that memory location what instruction is there, that will be executed after branch instruction, but not instruction 2. So this is what is all about some terms and actions involved in execution of branch instruction, be it unconditional or conditional. So for unconditional step 4 they have given, for conditional only step 4 will change, all remaining 4 will be same. Okay, those 5 steps of control sequence used for execution of unconditional branch instruction we shall see now. After knowing data path organization inside a processor and input output gating needed for register, we shall discuss on the control sequence for an unconditional branch instruction. So it has 5 steps of control sequence. First, second, third are required to fetch the branch instruction from memory into instruction register of the processor. 4 is used to execute. Then fifth will store the target address what is computed into program counter. So that to target address the program control is shifted instead of next instruction. A branch instruction replaces the contents of PC with the branch target address. This address is usually obtained by adding offset X, which is given in the branch instruction only, to the updated value of PC. Means 46 will be given in the branch instruction only. It is added to updated value of PC means 2004. This is from previous example what we discussed. Okay. Figure 7.7 gives a control sequence that implements an unconditional branch instruction. Processing starts as usual with the fetch phase. This phase ends when the instruction is loaded into the instruction register in step 3. The offset value is extracted from instruction register by the instruction decoding circuit, which will also perform sign extension if required. Since the value of updated PC already in Y, the offset X is gated onto the bus in step 4 and an addition operation is performed. In step 5, the result, which is the branch target address, is loaded in PC. The offset X used in a branch target address and the address immediately following the instruction. Okay. So these 5 steps of control sequence explain how when branch instruction is executed, instead of shifting the program control to next instruction, it is shifted to branch target address. And in target address memory location, what instruction is there, that will be executed, not the next instruction of branch instruction. But how in each step of control sequence the actions are performed, we shall see. Then only we can understand these 5 steps. Next, how actions needed are performed in each step of control sequence one by one we shall see. Okay. PC out control signal. PC was holding branch instruction memory address, that was 2000 in the previous example, because in that memory location 2000 branch instruction is stored. That has to be brought to instruction register now. This is accomplished by 3 steps of control sequence. In that, the first step of control sequence we are seeing. So PC out means in PC 2000 first instruction address, branch instruction address was stored, that is outputted means it comes on to processor bus. Then MAR in, that is saved in memory address register, that is also available on B input of ALU. Then read signal is given, this is control signal that goes to memory, because the instruction stored at 2000 has to be loaded onto IR register here. At the same time, select for control signal is given. So constant 4 comes at the output of MUX as A input to ALU. Add, that is the control signal to ALU. So 2004 are added. So that will be available at the output of ALU. Z in means 2004, that is next instruction address will be stored in Z register. Next, in second step of control sequence, Z out, a next instruction address, that is put 2004 onto processor bus. PC in, that will be saved in PC, that is program counter. Okay. Y in, at the same time it is also loaded in Y in register. Wait for memory function complete. So memory 2000 was asked to put its content, that is branch instruction, onto data lines. Processor will be waiting. When memory puts its content, that is branch instruction, onto data lines of external memory bus, MDR out signal is given. Because MDR in E will be always active, that instruction will be taken from data lines into MDR. When MDR out is given, that comes on to internal processor bus. IR in control signal, that it will input into instruction register. This is how at the end of third step of control sequence, branch instruction which was stored in memory 2000, that is brought to instruction register. In step 4 of control sequence, this is offset field of IR out, means from instruction register offset is given. So that is plus 46 was given in the previous example what we discussed. Where it goes as B operand because it is there on the processor. Naturally it will be available without gating as B input to ALU. Add. So add means what was here? 2004 was here. So through mux it will be available at A input. Then add means 2004 46 they are added. So 2050, that is target address will be available at the output of ALU. Z in means that target address will be stored in Z in register. Z out, that target address 2050 will be put on to internal processor bus. PC in, that will be inputted to program counter. End. So what is the end? So end of 5 steps of control sequence. Now PC is holding 2050, that is target address. This indicates that when branch instruction is executed, it gives the offset. It gave there 46. It was added to updated value of PC, that is 2004, and it became target address 2050, and PC is pointing to 2050 now. Hence from that memory location what content is there, that instruction will be taken for execution next, not 2004. This is how branch instruction shifts the program control from next instruction to target address instruction. Okay. So here branch instruction is unconditional. So these are the 5 steps of control sequence. Okay. If it were conditional branch instruction, then only this part would be added to 4th step of control sequence, which needs the checking of conditional code flags in the status register. So depending on the condition, if it is satisfied, the program control would be shifted, otherwise no. So this is the study for both unconditional and conditional. With 5 steps of control sequence what we discussed, that was for unconditional, and 4th step in that if we add this, the whole of the discussion will be for conditional branch instruction execution. Okay. So that is the completion of discussion for this question. Write and explain the control sequence for execution of an unconditional branch instruction. And we did for conditional also. So what all we discussed in this? First, the 5 control sequence which are required, 5 steps of control sequence. And to understand that, we went for data path inside the processor, then input output gating for the register. We took one example for branch instruction and we came to know what all terms and actions are involved in that. Then we concentrated on 5 steps of control sequence one by one in detail, how they perform the actions needed for execution of unconditional branch instruction. Okay, then we extended the discussion to conditional branch instruction execution also. That completes the discussion. I hope you understood. Thank you.